So there's this guy, Peter Higgs, and here he is. Dr. Peter Higgs gave us the answer to one of the most difficult questions of physics that we ever asked, that where does mass come from? Like, what we know that there is mass, and we know that that is something that things have. Like, we know it's one of the elementary things in nature that matter has mass, right? Any physical body that you have, it will have mass, and there were two different ways in which we defined it. So we have studied kinematics. So we can define mass in the amount or the ability of a body to resist change in motion. So we can say that mass is basically the ability of a body to resist any change in its motion. Like, if it is stationary, it wants to stay stationary, doesn't want to move. So when you try to do that, it applies some resistance. So, and that resistance is mass. So if something has high mass, then you will have to overcome that very high resistance when you're trying to move it. And if something has low mass, then obviously you can move it with very little push or pull. So that is what mass is. And it's one of the fundamental things, as I told you. Okay. So now the other question comes is that isn't that inertia? Like, didn't we say that inertia is the ability of a body to resist change in its motion, right? And what is mass then? And how is it related to inertia? So basically, inertia is that ability, and mass is the amount or the extent anything has that ability. Okay? और मतलब कितना वो उसको चेंज करती है वो mass है. How much does anything have inertia? How much inertia that thing has is its mass. Okay? And so it becomes a more of a circular thing. Like, things have inertia, and how much inertia they have is mass, and mass is a measure of the inertia that that thing has. Okay? And that is just one method of looking at mass. There's another method of looking at mass, that how much gravitational pull does that thing have? Okay. Or another way of looking at that thing is how much gravitational pull can that thing apply on something else? That is also mass. So it is how much is the ability of a body to resist change in motion? That's mass. Or how much gravitational force it can exert? That's also what mass is. And that is how Sir Isaac Newton defined mass, that is how much gravitational force anything can apply, that is mass. But still, we don't really know what it is. Like, we know that that's something that things have. And one, if you have more mass, then it's hard to move that thing. And two, if something has higher mass, it will have a higher gravitational force, right? So we know that thing about mass. We know that mass, if something has it, and all physical things have them, then they're hard to move. The more mass they have, the harder they are to move. And the more mass they have, the higher their gravitational pull, right? So that is the simplest level of how we have been able to define mass. Okay. Of course, we can then further work on that. And you might have seen documentaries in which they define mass in terms of energy, that mass is the ability, or mass is how much energy something has trapped in it. Similarly, another way to describe mass would be that how much does it curve the space-time continuum? That is something that you study, I think, in, I don't know, first or second year of university. So you'll study there that there is a thing called space-time continuum, and how much anything curves it. Like, that thing, if you place something on it, it will curve it. Like, if you have a mattress and you put a heavy ball on it, okay, so if you put a ball on a mattress, that mattress is obviously going to bend a little, right? So how much does anything do that to the mattress that is space-time continuum? That is mass. Okay. So mass in space-time. Let me find a good visualization of that. So yeah, this one is good. So imagine that the universe is made of this foam-like substance on which you have. Uh, so this is the space-time curvature. This thing. So the more heavier something is, the more it bends that space-time thing. So for example, this is supposed to be three different masses. So that yellow one is the heaviest of these because it bends the space-time the most. And then there's the orange one because it bends it a little less. And there's this red one which bends it a little more. And the idea of why things move, for example, why does Earth rotate around this, revolve around the sun, is simply that on one side we're saying sun has greater mass and Earth has smaller mass than that. So obviously the greater mass is pulling on the smaller mass, so it starts to move around it. Okay, obviously it goes through a transition, but then eventually starts to find an orbit and move in that. So that is one way we can see the effect of mass. Another way we can see the effect of mass, and according to Einstein's theory, that would be that it's not that Earth is moving around the sun. Actually, Earth is moving in this uh, bowl that space-time has had because of the high mass of sun. So Earth is just trying to get to the center, the bottom of that one, and it keeps on moving, eventually trying to get there. So sun is not actually pulling on it. Earth is just automatically moving according to that bend that it has. And so that's Einstein's idea of gravity, or Einstein's idea of what mass is and how it affects the bodies around us. Then there is also another way of defining mass, and that is also way beyond A levels. And the idea is that everything has a wave number and a frequency. So if you subtract the frequency from the wave number, what is left is mass. And that definition usually applies to really, really small things like electron, because that is where this is most prevalent, or even smaller things like photons or phonons or neutrinos or those kind of things. So there are many, many different ways of defining what mass is. And it all depends on the context or the field of study that you're currently in. So right now, because we are studying mechanics, we will stick with these two ways of looking at mass. So what is mass? Number one, it is how much does anything resist change in its motion. So if something is stationary, you want to move it, how much will it resist that? So we know that it will resist it, and that ability, that quality that something has, that property, that is inertia. Okay, so inertia is this thing that how much does inertia is this thing that things resist change in motion. So inertia is the ability of a body to resist change in its motion. All of this, it's basically inertia. Okay, so inertia is the ability of a body to resist change in its motion. That's what inertia is. And mass is how much inertia does anything have. So it is the measure of inertia of a body. Does that make sense? And another way of looking at it is how much gravitational force it can exert on the other thing. So obviously, if it has a higher mass, then it can apply a greater gravitational force. So for example, Earth applies gravitational force on the moon, and uh, the force that sun applies makes both Earth and moon move around it because sun has a greater mass. Okay, so clear so far what is mass and what's inertia. So where does Peter Higgs come in? Peter Higgs basically told us where this all of this comes from. Why do things do this? So he found a particle which is called Higgs boson. Okay, so Higgs boson. Boson is basically a family of particles. Like proton is a boson. No, proton is a hadron. Yeah. So he found that there is one particular boson which gives rise to the mass of things. And that is when things are initially made. So, for example, in the beginning of the universe, Higgs boson is the standard particle in the the quantum model of stuff that we have, that it gives mass to stuff. Okay. So Higgs was awarded Nobel Prize for this, and it is a big achievement, like really big achievement. Uh, you mean Big Bang Theory, the show? Yeah, I've watched it. The first few seasons, I really liked it, and then more people got involved and it got ruined. Yeah. Anyways, so that's mass. Now, there's another thing which is weight, and that's related to the second definition of mass that we have: how much gravitational force it can exert. So that gravitational force that anything experiences, that's called weight. So weight is the force or gravitational force experienced by a body. All right. So it obviously depends on the gravitational field that you have. So what exactly is a field? Field is a term we will use many, many times in physics, and field simply means the space. Yeah. So I was saying that Peter Higgs basically allowed us to understand where all of this comes from. And that's a very interesting story of how he figured this out in 1964, but the world actually got to know experimental evidence of this in 2018. So that's a long struggle for such a great mind and obviously his team. So I was saying that field is basically a region of space. It's the space around a particular body where you experience certain force. So, for example, if you're talking about magnet, then any magnet that you might have played with, you might have seen that it has a certain area or space around it where it can extend that force that it has. So it can attract stuff from maybe a really powerful magnet might be able to attract stuff from a few meters away, right? If you are playing with some toy magnets, then they might be able to attract things from maybe 1 feet away or something. So that is the space in which their magnetic field extends to, or their magnetic force can be experienced. So just like that, mass experiences gravitational force. So any mass extends that gravitational field around it. So sun has a gravitational field. So if there is a star that is really, really far away, it might not be that close in the gravitational field of the sun, which is why it's not attracted that much. Of course, gravity is a force that extends to even very, very large distances. Like I'm sure sun is extending its gravity to something that is at the edge of the universe, many 100 billion light years away. But the thing is, sorry, many hundred, maybe 100 billion light years. So why is that not being experienced? Why are we not attracting stuff from the edge of the universe? Because the force gets too small by the time it reaches there. So every field has certain area uh, where that force is significant, and then it starts to tamper with. So inertia is the ability of a body to resist change in its motion, and weight is the force that thing that has inertia, वो कितना weight experience करती है, वो कितनी gravitational fields experience करती है, that is what we call weight. Okay, so obviously that depends on the field that you're in. So for example, something that has weight on Earth will have a totally different weight on the moon. Why? Because the dominant gravitational force that we have on Earth is Earth's gravity. But when you get to moon, the dominant gravitational force that you have is moon's gravity. Because Earth and moon are almost 300,000 kilometers away. So by that time, the Earth's gravitational field is very weak, or the strength of that field is very weak, and their moon's gravitational field is much, much stronger. Okay, so whenever you're talking about weight, you have to talk with relevance to a particular gravitational body or gravitational force that you have, which is why whenever we talk about weight, we say that W equals mg. And I will talk about it tomorrow, that how do we get to this point that W is equal to mg. But for now, we are just saying that weight of anything is equal to the mass that it has, so that is how much inertia it can experience, times the gravitational acceleration. Okay, and gravitational acceleration, or another way to look at this, is gravitational force per kg. That's another way of looking at it. So G can be in newtons per kg, or it can be in, sorry, or it can be in meters per second square. So because we talked about units, so any of those units would be good enough for this. Okay. Now, Adina has a very, very good question. In fact, that is one question that occurred to many people many, many centuries ago, and they couldn't answer it until Sir Isaac Newton did. That why does, first of all, the question is that what exactly is gravitational field, and then why does the gravitational field strength of different regions like Moon or Earth differ from each other? So again, what exactly does gravity depend on, right? So that is, I think, the question that you've posed. And we have already answered it. Mass is what the gravitational force depends on. So if something has higher mass, it can exert greater gravitational force, which means the strength of that field depends on what mass that thing has. So because Earth has mass that is almost 6 times that of Moon, Moon, Earth's gravitational field will be 6 times stronger than that of Moon. All right. Similarly, Earth has mass, which is, I think, 2,000 times less than that of Sun, if I'm not wrong. Then we know that the Earth's gravitational field will also be 2,000 times less strong, or 2,000 times weaker than that of the Sun. Okay, so that's how we know. We can easily figure that one out. Oh, I'm sorry, I just checked. Sun is not 2,000, it is 1,000,000 times as heavy as the Earth. So that means Earth's gravitational field is 1,000,000 times weaker than that of the Sun. So it's pretty standard. Okay? So gravity depends on how much mass something has. And that's how we define mass as well when you're talking about gravity. So mass ho gaya, weight ho gaya. Weight depends on the gravitational force. And if something does not have any gravitational force, so for example, if something is moving around in the space and it doesn't really have much of any gravitational force to experience, then its G will become 0. And when G is 0, weight will be m times 0, which is 0, right? So weight will be 0 newtons. So you can have 0 weight, and that's called weightlessness, right? So we might have experienced that in terms of our opinions, the weightlessness, but physically we can also experience that if we are in a region of space where there is no dominant gravitational field. So for example, if you're an astronaut going out for spacewalk, it is possible that the gravitational field of Earth is too weak to register, and you can say that, okay, over here G is 0. It also means that G depends on the gravitation or gravity of something. So for example, if you're closer to the Earth's center, the higher you will experience weight. So for example, if you're at the surface, like sea level, you will have the greatest weight. If you move away, your weight will differ. Okay, so further you are from it, or when you're, for example, when you're flying, your weight is less than when you are uh, maybe on a beach or something. So it all depends on how far you are from the center of the Earth, and also how much your mass is, and those things combined will affect the weight that you have. Okay, so weight depends on gravity, and that's the important takeaway from this. But mass does not, because you see, nowhere did I say that mass depends on something. I'm saying mass is the measure of inertia in a body, and inertia is simply how much mass it has, right? So that's a circular definition. So mass doesn't really depend on it, and inertia, there's no machine that measures inertia. Similarly, mass depends on how much gravitational force it can exert on something else. Again, gravitational force depends on the mass, but mass doesn't depend on it, right? So just like that, mass doesn't get affected if you change where you are. So you can be on the surface of the Earth, or you can visit Mars or some other planet or whatever. But because your gravity or the gravity of that place does not affect mass, the mass that you have will still be the same. So while you can lose weight by changing your planet, you cannot lose mass. Okay. So that's the important takeaway from this, the difference between mass and weight. Another thing, weight is always because of some gravitational force. So because of that, weight is always towards some body. So for example, if I say that my weight is, I don't know, let's say 800 newtons, then my weight will be towards the center of the earth. So it has a direction to it. But mass, if I say, let's suppose my mass is 75 kg, then that mass does not have any direction because it doesn't depend on anything like that. So my mass is 75 regardless of where I am. And I can, if I try to say that mass is 75 kg to the north, that makes absolutely no sense because mass is a scalar quantity. So refer to the first lesson that we did. There are scalar quantities and there are vector quantities. So gravity is a vector quantity, it's a force. So weight, which depends on it, is also a vector. So weight is towards the center of Earth, Moon, Mars, whatever you're talking about. But mass is not. So mass is scalar. So that's another important distinction between mass and weight. Last thing in this discussion is density. But before we get to density, it's important to talk about what is volume. So volume is the space occupied by something. Okay. So that's what volume is. Obviously, you can reduce the space that that thing occupies. So for example, if you have a foam or you have, let's suppose you have a handbag and that handbag has some space. And usually when you buy handbags or any bag or any container, they usually have some volume written on it that this is this many liters or this many decimeter cube or something. And all that tells you is how much space it can have. But that does not mean that it will have exactly that much. You can reduce it. You can apply some force on it. You can apply some pressure on it. And you can compress that handbag or whatever you have. And that saves some space that you have, especially when you're transporting stuff. If you can do that to stuff, it really helps save space. But it doesn't affect its mass. So again, we have seen that volume depends on what that thing has, what that thing's dimensions are. So for example, if I have a table, it will be very hard for me to change the volume of that table unless I start to pack it and make smaller pieces from it. But as a table, it has a certain volume, a certain space that it needs. If my table is too big for a room, there's no way I can fit into that same room. It is already too big. So I will have to alter its dimensions or something, right? So volume depends on the dimension, but mass does not. I can put the same massive, I can have the same mass of another table which fits into that room. It might be smaller, but it will be the same mass. It can be. So how heavy things are, it's very hard to change them. But how big or small things are, there are ways to be smart about it. So volume depends on dimensions. So there's the whole geometry thing that if you want to figure out volume of something, you figure it out based on its shape. So there are two ways to do it. One is the geometrical method. And the geometrical method of measuring volume is that you take anything. So for example, I have this bag. Okay. So this is supposed to be a bag. All right. And what happens is that I will simply divide it into some shape. I'll be like, okay, hold on. This looks like a trapezium, right? And this trapezium has some parallel sides. This has some height. And this is also the width of this thing. So I can simply use this one. I'll call it L1 or L2. And I can simply find the volume of this because I paid attention in 8th grade geometry. But if you have a very different shape, so for example, if I have some other weird shape, like I have something like this, and I want to figure out, okay, what's the volume of this thing? So it will be quite hard for me to, quite a challenging thing to figure out its volume. So geometry helps us, and I can figure this out. I can find ways to approximate it, or I can find ways to find it to a certain level of precision, but I might not have a very good quality answer when I'm talking about this. Geometry might not help me there. So then we have another method which is called displacement method. So if you can't use geometry to your advantage, use the displacement method. And what displacement method depends on is that you take something for something that you can easily measure the volume of. So for example, I can measure the volume of water. And then I take whatever thing I have and I put it into that thing, into the volume of water that I have. So obviously, volume adds to it. Okay, so you take two things, you combine them together, their volumes will add, right? So what happens is that I have, let's suppose, a container in which I know that, okay, I have water to this level, and this is, I don't know, 100 cm cube. And now what I'm going to do is I'm going to take this thing, place it inside. Okay. So I placed it inside. And what suddenly happens is that the level of water will rise. Okay. So it rises to this level. And when I see this, okay, this is 120 centimeter cube. So what has happened? Basically, this change in volume is coming because of this thing. So I can simply say that my water is still the same. I did not add more water, right? So 120. So it's like this. Volume of just water was 100, right? Cm cube. Volume of water plus this object, 120. So just the volume of object. This is simple maths. You subtract it. So you know that it is 20 cm cube. Geometry might not have helped me as much, but I can see that using a displacement method. And because I'm displacing water, I will call it water displacement method. Now, people have made a very smart or a good container for this. This is called a Eureka can. Okay. So Eureka can. And what you do is you fill it to this level and you put a small empty container next to it. Now, if I want to measure the volume of this thing, all I have to do is move it in here. So obviously the water level will rise. But because there is a hole in there, instead of rising, water will spill into this one. And here I can easily measure how much volume it has. So it is 20 cm cube. The advantage of Eureka can is that you don't have to do the math, because it is possible that somebody might make a mistake when measuring the initial value or the final value or subtracting. So people can make errors. So this reduces your error because you just have to do one measurement here. This method depended on two measurements, okay, and one calculation. So every time you do something, it is prone to error. So two measurements means that there are two times you can commit an error. And one calculation means you can also make an error in that one calculation. But with Eureka can, you're just taking one measurement and you know the volume right away. So that Eureka can basically displaces it and in turn spills it over to the empty container. And that's how you find the volume of stuff. So now we know that how we can measure mass is you can put it on a scale or a balance and you will figure out the mass. And with volume, you can either you do the geometrical approach and you can break it down into some shape and do measurements of those and do it, or you can use the displacement method and you can displace water. Sometimes we displace air. For example, if I'm trying to collect any gas, we might use water displacement, or if we can't, we might use displacement of some other gas or something. So there are ways that exist to refine this process. And Eureka can is also a really good technique for this. All right. Named after the famous Eureka expression of Archimedes, who was an ancient Greek or Roman philosopher. I think he must have been Greek. Romans ne kuch nahi kaam kar diya Ahmed. So Archimedes was a Greek philosopher and he figured out this displacement technique. Okay, so we now know volume, we now know mass. The next thing that we have to figure out from this is density. And density is mass over volume. So this formula is also the definition. So whenever I give you a formula that is the definition, I will put a triangle on it. Okay. So this triangle simply tells me that density is mass over volume. or mass of an object divided by volume of that same object. That's density. Density hai kya? Density is how heavy does something feel. Okay, so it's more, you can easily measure density using two measurements. You measure volume separately, you measure mass separately, and density is simply how heavy something feels. So for example, uh, you if I give you two containers, or two, let's suppose I give you two crystal balls, and I say, okay, how heavy are they? And one is made of glass, and while the other is made of some very light plastic. Then you can easily figure out that, okay, they're both crystal balls, but one is much lighter than the other. And when I say that I gave you the same size of those crystal balls, then basically what I'm saying is that they have the same volume, because they're the same size, right? And we have seen that volume depends on dimension. So they're the same size, but one is heavy. And why is it heavy? Because it has more mass, it has more particles in it, it has a higher inertia, it can exert a greater gravitational force. Okay, so that is why it feels heavy, because the mass that is per unit volume is much higher than the mass per unit volume in the other thing. So usually we know stuff that is like metals, they have high density because they have strong forces packing the particles closer to each other. Just like uh, osmium is the heaviest, the densest metal that we know of, because the metallic bonding in it. And I'm assuming you all study chemistry. Munib, do you study chemistry? And Malika, do you still study chemistry? Okay, so you might know about these forces that we have in stuff. So, for example, these forces pack atoms together or molecules together. So, the stronger the forces, the greater the packing factor, which means the more mass you have in the same amount of space that you have. All right, so that makes stuff more dense. Usually, people assume that dense things are also going to be hard. That's just a correlation, doesn't really mean anything. Okay, so it's not that dense stuff has to be hard. It can be, but doesn't have to be. The two don't really have anything to do with each other. So, for example, our bones, they are dense because they make up most of our mass, and they have minerals and all that in it. So density all comes from how much mass you fit into how much volume that you have. Okay, so for example, neutron stars are one of the densest things in the universe. And neutron stars are like, if you take a teaspoon of a neutron star, then it will be, I think it will be the mass of around, I'll have to do some math for that. So let's try to, what is a, so if you were to divide 100 with this, how much do you get? अच्छा चलो इसको भी छोड़ दो. You can think of it like this, that mass of one teaspoon from a neutron star, okay, will probably be how much? A trillion kgs. A trillion kgs. That is, so 3 teaspoons from a neutron star will weigh more than Earth. So what am I saying? I'm saying that the 3 teaspoons that you have, so teaspoon is here a unit of volume, and the mass from the neutron star that you get is so heavy that for 3 teaspoons, it's going to be more than mass of the Earth. So that's how heavy those things are, neutron stars. You can search about them. All right, so that's density, how closely something is packed together. Neutron stars are one of the more dense stuff because they have a very high packing factor. ठीक हो गया? So that's it.